Hello everyone, I hope you had a great break from lunch. So now we'll be going to talk about stack exploitation, right? So previously you have learned about the ELF, the memory layout, what are addresses, and some basic assembly. So now we're going to put that into practice by actually doing some exploitation on the stack. So let's recall, right? So previously we have mentioned that the stack is used for managing function calls and local variables. And one of the variables stored in the stack is the return address, which specifies the address that is popped into red when you call the instruction to resume code execution after calling a function. So what happens if we're able to overwrite the stored return address on a stack? This is what we call a buffer overflow, one of the most primitive vulnerabilities researchers discovered back when programming was still a very new thing. So let's just say we allocate hex 20 or in decimal 32 bytes of memory on the stack for an input buffer. So what happens if we read more than 32 bytes into the input buffer? Or perhaps more importantly, what happens if we write more than 32 bytes into the input buffer? So here's a visualization of the stack. So we go from high address at the bottom to low address at the top. And as we write our user input down the stack, we realize that if we are able to write beyond 32 bytes, each box here represents 8 bytes, we realize that we can actually write into the saved RBP and saved RIP of the program. So actually, we can overwrite the saved return address on the stack. And as we know from previously, seeing how call and ret work together, the return address determines where the program jumps to next. So we'll perhaps by overwriting this stored RP, we're able to redirect code execution to where we want it to. So this means we can set RP to whatever we want, and we can control where to send the program next. So now I'll be walking through the challenge, Red to Win. In your CTFD, you should have been able to download the challenge called Red to Win, here to Red to Win. So I've already initialized the challenge with pwn in it. But if you have not done so, you can go ahead and run pwn init in your terminal in the folder of which you downloaded the challenge in, of which the folder that contains the challenge, you can run pwn init in order to initialize it, but I have already done so here, so I will not be doing it. So we can take a look at the code. Actually, the code has been provided for us. If we look at the distribution, we have the code in main.c, right? Not sure how familiar all of you are with C syntax, but if you have done programming, a lot of this should be rather intuitive to grasp. So we have our main function at the bottom right here, and it does this setup thing. We can ignore this. We don't need to know what it does currently. Let's put our effort into trying to understand what Valm does. So we can see that Valm creates a buffer, hex 30, on the stack. So we have hex 30 size buffer on the stack. And we put please get your name. And then we get the buffer. So what gets does is that basically it reads your user input into the variable, in this case buffer. But you notice that we only call gets with one argument, and that's the buffer. This means that gets will read all the way to the end of the input and put it into buffer. Do you see the problem here? Because our input can be infinitely long, theoretically, we can override buffer with a very, very long payload and overwrite data beyond the info buffer. So, I'll zoom in here, sorry. So, what we can see is that actually with this gets, we are able to overwrite beyond the buffer into the stack frames RBP and the RP. And we have a win function over here. So the win function basically just calls XF. XF is a Linux syscall that runs a program specified here. So we specified binsh, which is the Linux shell. And so by redirecting execution to the win function, we win by getting a shell. Yep, so what we want to do is that we want to have a very big buffer that overrides all this input buffer with the REP and overrides the saved REP with our return address. So we can take a look at this in GDB. So in GDB, we can do this as main, sorry, to see the disassembly of a function. So for example, this case main, actually we're interested in val, so val. And we see that we call gets right over here. We call gets, and we can set a breakpoint here to look at how the stack will look after we have entered our input. So we can hit R to run, and oh, apologies. Apologies. Yeah. Okay. Let's just run. We broke at the gets, so we haven't called gets yet, but let's just do so now by stepping through with ni. Ni allows us to step through the instructions one by one. So we can step through with ni, and now we have called gets. So now the program is waiting for us to enter our input. So let's just put a very big nonsensical input inside. And okay, so we've stepped one step and we have done the call. So we can now look at the stack with the command telescope, and we can see that our input has actually written the specified hex 30 size. So if you look back in our program, our buffer is actually intended to be only hex 30, but here we can see that we have written over all the way from here to here. So clearly we can see that we have buffer overflowed and overwritten data below on the stack. And so one of them is actually our return address. So if we just step over a bit more and step all the way to red, right, and look at the stack, you can see that, as we know, right, well, red does this pop RP and pop RP. So what it does is just take the address that it wants to jump to off of the top of the stack and put it into the instruction pointer, and that will allow us to return control the function to its caller. But in this case, if we take a look at the stack, we can see that it's actually being overwritten by our garbage data over here at top. So this proves that we are able to overwrite the return address, and let's just continue execution from here. And we can see that the program has stopped due to 6F. So 6F is basically a crash in Linux, and the program crashed because if we look into the info registers allows us to see what the values of the registers are set, right? So if you look at actually because we are trying to pop this very big value, not say very big value, but this overwritten value with our jumbled data into the RP, the program doesn't know where to go because this random data address clearly does not exist. So this has resulted in 6F because the program cannot find a valid assembly code, a valid binary code to execute at this address. So that's basically what's happening. So what we want to do instead is, instead of overwriting the return address with our random address, what we want to do is to surgically do it such that we override this with the return address we want to return with anyways. So we can try to do that in our code editor. So For the purposes of making our exploit development easier, we use this thing called Pwn tools. Pwn tools contains a lot of quality of life helper functions for us to do binary exploitation. So you can see here that we load the executable into the solve script and we define a connection. So if we pass in a local argument or a GDB argument or both, we will create the process and if so, attach GDB to our local process. Or else it will run default against the remote. So the remote is the netcat address you see on the CTFD. There's a separate video detailing how you can connect to the remote as such. So let's just do so here we have a main function and we see good luck pwning over here. So this is where our exploit is going to be written. So what we can do now is we can set up payload of hex 38 length. Why 38? Because we want to smash the input buffer, hex 30, sorry. We want to smash the hex 30 input buffer as well as the hex 08 RBP. So once we have filled this in with hex 38 data, the next bytes we write will be in the saved RIP. So we can do payload plus equals to P64 exe P64 and we want the address of the win function. So what we can do is we can go back to GDB and we can do info functions and this will give us the address of win. So what P64 does is that, as you know, our computers store data in little endian, right? So it takes our big endian visual representation of the number and converts into little endian bytes. And that's also why we use byte strings, because we want to send Pwn tools works by sending in raw bytes into the program, and we want to construct our payload at the byte level to ensure that our custom payload is surgically targeted to overwrite the saved RIP. So P64 is just a nice helper function to help us convert from big endian to little endian, and we can append that output to our payload. Afterwards, we can use r.sendLine after to send our payload. So what this does is that it will wait for so what we want to do is want to send the input after it's printed out name and new line. You can see that there's a new line here because our input character is on the new line. So we can type name with a new line \n payload. So what this does is that it waits until the program prints out this, then it will send the payload. So this is for timing, consistency. We always want to use sendLine after because we want to ensure that we don't send our payload too early before the program has printed out the necessary stuff. So now we have plotted this payload. We can try and run it. We'll solve py local. Local argument is important here because as you see here, only with local does it spawn a local process, or else we'll just use the remote. And we don't have the remote set up yet, so just solve py local, and we can see that we have popped the shell. Great. So if we attach GDB to it, and we just apologies. So if we were to just set a breakpoint at the over here after we call gets, and you don't need to. So I'm going to run GDB attached to my solve script now for you to better visualize what is happening. So we can see that we have stopped at a breakpoint where we have gotten our input. If we do telescope again to look at the stack, we can see that our overwrite has written over hex 38 bytes of data, and our return address over here is overwritten to win. So instead of jumping back to main after it concludes, it will jump to win at hex 38 because we have overwritten the saved RIP at hex 38. And because of that, when we press continue, we have won, and we're given a shell, and we do ls. Oh, there's a piping issue with this. Yeah, do ls, you can see that we actually get the shell. Yeah, amazing. So this is how we can use a buffer overflow exploit to very simply overwrite the return address and therefore get a shell. So you may take some time to try this on your own, and afterwards we'll move on to the next one. Okay, so now that you have understood what a red to win does and have hopefully tried to attempt the challenge on yourself, we can now take a look at mitigations. So programmers are not stupid, right? They know that there are hackers, there are cybersecurity researchers trying to break the program, and they want to prevent us from doing our jobs by implementing mitigations. So some of these mitigations are like, say, to make our lives doing exploits more difficult, and hopefully in a bid to perhaps secure the program a bit more even when the traditional logic breaks down. So one of the mitigations we're going to look at today is position independent executable. So PIE stands for position independent executable, and it randomizes the address at which it is loaded at runtime. This means that we can't hardcode addresses into our solves. So now what this mitigation, changing, randomizing the place that we upload our data, we don't even know where our code will live in the memory because the address will be different every time. So we cannot overwrite the entire address now because we don't even know at what address the program will be loaded. So what can we do now? So if you go to CTFD, you can see this challenge called Red to Win High. Yeah, if you see, you can see the challenge Red to Win Pi. So we have a little activity over here. You can try to brainstorm some solutions to defeat PIE in this challenge. You have 10 minutes, and unfortunately, as this is a recording, you are unable to ask for assistance, but if you are confused or anything, feel free to open a ticket and we will respond. You may pause the video now to consider how you might want to approach this mitigation. I strongly recommend you to open GDB and play around with the breakpoints and stuff. So specifically for this challenge, when you run GDB, you need to do set disable randomization off in order for PIE to work, because by default GDB disables PIE even if the binary has it enabled to make it easier for debugging. But because we want to see how PIE affects the binary, we want to do set disable randomization off, and you might want to run the binary a couple of times to see what changes, what doesn't change, and how we can exploit that knowledge to better solve the challenge. Alright, so I hope that you had some time to think about how you want to approach this, but basically PIE works by loading the entire .text segment to a set offset that randomizes for certain bytes. So that means the last 3 digits, aka nibbles of address, remain unchanged. So for example, in GDB, you can see that all the bytes in front here, all the digits here, aka nibbles, all the nibbles here are randomized. So randomized 5557, 5558, etc. But the last 3 nibbles, 000, 000, these will remain unchanged when you set the entire offset. So what you need to know is that in PIE, the first 13 bytes are randomized, but because of this feature, the last three numbers of your hexadecimal representation of your address remains unchanged. So we actually can see this if we just do break main, and we just run it a couple times. We see that here main is at something 266. We just run it again. Oh, it's another random address 266. Run again. Oh, it's randomized again, but still 266. Randomized again, but still 266. So we see that by running the program multiple times, even though everything in front here changes, the 266 at the back does not change. So that's what we mean by the last three nibbles does not change. And so that means we have a 1/6 chance of getting the fourth nibble correct, because we need to write 4 bytes. We need to write 2 bytes, right? We can't write half a byte, because bytes are the smallest units we can write into in our payload. So when we write 2 bytes, and because we know that the program is in little endian, right? So the last bytes become the first bytes we write. The last bytes we see on the screen become the first bytes we write to the program. So 66 and 32 will be the first bytes that we write into the program, and we can just do a partial overwrite of these 2 bytes. We don't need to touch the rest. The rest remain the same as the randomization, but we only overwrite the last 2 bytes as a partial overwrite. And because we can only write in terms of bytes, we need to guess this digit, because only the last 3 digits remain the same, but this fourth one over here will be randomized by a PIE. So when we do this 2-byte overwrite, we just pray and hope that we get really lucky and get a 1/16th chance of getting the fourth nibble correct. Yeah. And as this approach requires us to guess 1 nibble, it makes it highly inefficient, and also showcases the efficacy of PIE as a decently effective mitigation measure, right? Because if you think about it, if you have like tens of addresses that you need to hard code into your payload, when they get randomized by PIE, your odds of 1/16th and 1/16th and 1/16th will stack until it is functionally impossible to get your payload to work. So let's just take a look at how we can implement this in our code. So, unfortunately, I did not do pwn init. So I've just quickly done pwn init over here, and we can see that because I'm using my custom version of pwn init, you saw that I just did unstrip right there. Because the VM we provide does not provide a custom version of pwn init, we provide the standard version. So you just need to do pwn init without the no unstripped argument and wait for it to unstrip the libc. So what we can do here is we can see that in our binary, right, we have PIE. So our win function in this case is now called PIE instead of win, and we have a vowel and we do read, yada yada yada. Okay, so what we can do is the same payload. We can set up a payload of hex 38 length. Then we can add our partial override of our, we can do the partial override of our address. So we open GDB, we do info functions, and get the address of vowel. So because the entire binary is offset by a randomization, the relative offset from vowel to the start of the binary where it's loaded is the same. So we can see that vowel is loaded at offset 11 CD, and because only the last 3 nibbles will be randomized, what's 1 CD will remain the same, while we have to guess this one. So we can just write it in a little endian form. Remember, it is backwards, so it's reverse, so it's xcd x11, and we're going to guess the last one. We're going to guess the 1 over here as 1, and we can then send. Here we're going to use send after, because because send line after will send a new line, aka this thing, a new line at the end of our input, but we don't want that because we only want to overwrite partially 2 bytes. So we use send after instead of send line after to make sure that we don't send the extra new line. So now we have our payload ready. We can try it out in our terminal. Because this is a luck-based script, we have a 1/16 chance of getting it correct. So let's just pray that we get lucky. You might need to run it quite a couple of times to get it to work. That is quite normal. The odds diminish around like 20 to 30 times if I am not wrong. So we just have to do it quite frequently. Yes, does take a lot of luck to get it to work. But once it works, it should be quite obvious. Did I write my source script correctly? Yeah, it should be correct. Wait, apologies, I think I copied the wrong address. Yeah, I copied the address of Val instead of pi. So pi is actually 11A9. So instead of CD is A9. So apologies. So we do hex A9, hex 11, hex 11. Yeah. So let's just try again. Takes quite a bit of luck. And you can see it's actually quite effective because our byte brute force is not actually going to, it's not actually working very well as it sees right here. Keep on. So let's just try to brute force another byte. Maybe perhaps it's kind of hard to get a 1 over here for some reason. Oh yeah, so after a lot of brute forcing and some fiddling with the bytes, we finally get our shell. So yeah, so this is how we can do a partial overwrite to overcome PIE, but at the same time, we have 1/16 chance of getting it correct. And yeah, it just showcases really how effective position independent executable is in mitigating some of these like fixed address for solve scripts and exploits that we have. So yeah, now that you have tried out the PIE challenge for yourself, we will now move on to the next one, right? So what if we don't have a win function? Most programs aren't so nice as to provide us with, oh, here you go, here, have a win function that I'll just magically give you the shell, right? No developer is stupid enough to do this. So what happens if we don't have a win function? What can we do without a win function? So what we need to do is that we need to create the conditions to pop our own shell. So what can we do to create our own shell? Let's just do a quick introduction to memory permissions right here. So as you know, like in this file system, we have read, write, execute permissions for files, right? Similarly for memory. So for a memory space allocated, it is tied to a permission. You can set whether we have read, write, execute permissions. So for example, here is the memory permissions for the previous challenge, and we see that here under perm, the RWXP for the stack, R for read, W for write, X for execute. So it seems that apparently we have execute permissions on the stack. So what if we just write our own code that will pop a shell on the stack and send our program to execute it? But in order to write our own code in assembly, we need to know how to set up function arguments. So in order to call functions, we set up arguments, and in x86-64, arguments are set up in the following order: RDI, RSI, RDX, and the rest. You really don't need to know beyond the fourth. Only the first three are the important ones. So RDI is the first argument, RSI is the second argument, RDX is the third argument. So to help you better visualize, here is a function, hello, that takes in three inputs, A, B, and C. So input A as the first argument will be stored in RDI. Input B as the second argument will be RSI. Input C as the third argument will be in RDX. So before we call a function, we need to set its arguments as such by putting the respective values in RDI, RSI, RDX in order to call it with the our own specified argument. So another thing we can use is syscalls. So on the Linux platform, syscalls allow us to execute certain kernel commands, and they can be invoked by the syscall instruction. So we look to RAX for the syscall number to execute, and for context, to just contextualize, we can take a look at the syscall table here. So if we go down, we can see that for each syscall that Linux has, there's a number which corresponds to its RAX value. So by specifying the correct RAX value, we can specify a syscall to call. So we search down for this very peculiar syscall called I.YCEP. So if we set our RAX to hex 3B, we can therefore execute the I.YCEP syscall, and it takes in a file name, argv-mp. These can be null, we don't need to consider them. These need to be null. But the file name is the most interesting one because this specifies what binary we're executing. And if we put a pointer to the string binsh, we are able to run I.YCEP with the syscall and therefore pop a shell. So we can set up arguments to syscalls like functions. We can basically think of them as functions, and one of them exists as one a user specified program. So what we want to do, we want to set RAX, RDI, RSI, RDX to our specified syscalls, to our specified arguments, and then we call the syscall instruction, which allows us to call the I.YCEP syscall with our specified arguments. So let's just walk through how we can do this with the shell coding challenge. It is available on the CTFD as for shell coding. So let's just open up our code editor over here. So here we can see that the program gives us our buffer, and we have a buffer of hex 30. And it says yada yada yada, and it prints out the pointer to our buffer. So what this printf does is it prints out a pointer to our buffer. So we can see that by just running the program here, you see that this is where our buffer starts. So what we want to do is that we want to write shellcode such that we fill this buffer, and then it will jump back to this buffer. So we write the shellcode to the buffer, and then we set the RP to an address on the stack where we have written our shellcode. So in order to do this, we will be writing the shellcode below the saved return address, because if you will visualize, we only have hex 30 on the buffer, and then after that we have 8 bytes for the save RBP, and then we have 8 bytes for save RIP. Hex 30 may not necessarily be enough to write an entire shellcode. So what we can do is that we can actually put our shellcode right below our instruction pointer, And instead of our instruction pointer pointing back to the top of our buffer, where we would think we would put the shellcode at, we can actually point it to at the hex 40 offset, because hex 30 plus hex 8 plus hex 8, hex 40 offset to our RIP in order to point to the shellcode at the bottom of our RIP. So, in order to do this, we can go into our solve script and set up the payload. So in order to do this, we need to receive the pointer that has been printed here, right? So what we can do is that we can actually get the leak by doing receive until here, and then we can leak equals to int or receive line dot strip 16. So what this does is that if we go back to our program, we can see that when we execute it, it says your pointer order stored here. So what receive until is that it will receive the data that it prints until here. So here's where they'll cut off receiving the data, and afterwards we want this data to be received. Then we receive this data, which is our hex address over here, receive line, and then we strip by removing the new line at the very end. You can see there's a new line, and then we convert it to an integer. We convert it to an integer by taking a hex input. So this is a hex number. We can convert it into an integer by doing int with 16 as an argument. Yeah. So then we can use a sleek to know our shellcode address. So we can do payload plus equals to p64 leak plus x40. Then we can do our shellcode over here. You don't need to know exactly what the shellcode is doing. You just need to know that by putting this code inside, we can execute it on the stack, right? Because the stack has execute permissions. So we can execute the code on the stack, and therefore when we return, instead of when we put the return address on the stack, we're able to execute it and therefore create the own conditions for us to get a shell. So we can do yeah. So basically we can run this code. Did you know that what this code does is it set up the registers and call it such a way that we have bin sh. We have RDI points to bin sh, and we have RSI and RDX at 0. When we do a syscall, we are able to pop a shell by running XF. So do send line after, the send line after, order bin payload, and then we can try to run this. Oh, apologies. Move is MOV, roll MOVE. Yeah, and you can see that we actually pop a shell. So here you can see you can see the shell has been popped over here. So now we can see how we can use shellcode in order to write our own code onto the stack and execute it in such a way that we get a shell. So now that we know how we can use shellcode in order to gain remote code execution without a win function, why do people not shellcode these days, right? In the past, we used to see a lot of people using shellcoding as a method to get code execution. But recently, if you look at the recent CVEs and binary exploitation techniques, we see that shellcoding has become perhaps less and less relevant these days. So one of the prehensions is that today most programs are compiled with the NX bit set, which basically makes the entire stack non-executable. So even though we can write our code onto the stack, because we don't have execute permissions on the stack anymore, we are unable to execute code on the stack. So other than shellcoding, what else can we do in order to pop a shell? So what if we didn't have to write our own instructions? What if, even better, the binary gave us the instructions that we need to pop a shell? So, and congratulations, you just invented return-oriented programming. So what is return-oriented programming, right? So we can think of each instruction in the binary as analogous to a Lego brick. And the binary specifies a specific way we should assemble them, like a manual. So let's just say we have this very cool Lego set, right? But there's nothing stopping us from assembling them in another way, contrary to what the manual specifies. So what if we reorganize the instructions in the program to give us a shell? So let us take a look back at our stack visualization. So here, as you can see, we have a buffer overflow, and we can overwrite the RP to what we want to jump to. On the left here, we have this cool code blocks, right? These blocks of tiny pieces of code that we can redirect execution to. So we can actually put the address of, let's say, the pop RAX code block into the save RIP, right? And because the address of pop RAX is popped off after the ret, then top of the stack now becomes the value we want to put in RAX. So we actually can put the value of RAX below the address and therefore pop the address that we want to put into RAX from the stack. And because the code block then calls a ret, it then again looks back to the stack to see where to return to. And oh, cool, if we put another address below the value we want to put in RAX, we get to specify another address to jump to. So you can repeat this chain for the different code blocks. So for example, here we have pop RDI. We can put address of pop RDI into the area of which it will be popped off, and we will redirect execution to pop RDI. And because all of these top values have been popped off, right? The value we want to put into RDI will be on the top of the stack. So next, when we want to do when the pop RDI executes, it pops the value here into RDI, and then it calls ret, which, because this value is popped off, the top of the stack is now here. So it will look at here for an address and pop it off the stack. So you realize that as long as we're able to chain these code blocks together with rets, we can continuously do execution of these very small code blocks in order to perhaps do something with all the instructions before the ret. So that's the basic idea of return-oriented programming. The small code blocks we see on the left are what we call gadgets. And most crucially, they all end with a ret. So by chaining gadgets together, we can set values and execute code that results in a shell. So now we'll do a quick walkthrough of Red to Win Revenge. It is available on the CTFD, and you should see it here. So it's 5 Red to Win Revenge, and you should be provided with this distribution. So we can just do this. We can do poll init to just quickly initialize. Alright, so now it has been initialized with the solve script. We can open it in our editor. So what we see here is that what we see here in our program, right? Our main.c is that we have a function called win. It takes an argument score, and it checks if our score is larger than this very big number. And if it is, we win. If it's not, then we lose. So the rest are pretty standard buffer overflow vulnerability thing. But the thing is that we need to set the first argument when we call the win function to a score. So if you recall previously from when we tried to do shell coding, that the first argument is stored in RDI. So, and you can see here, down here, the gifts. Very nicely, you have been provided a code block. No, sorry, assembly snippet that does pop RDI red. So what we want to do now is that we want to search around for gadgets that we might want to use from the program. So what we can do is we can actually use this tool called rp gadget, and we can run this command to pipe the output to a text file gadgets.txt. So we can run it and it will search for all the gadgets that we have. So if we take a look, we see that we have all this list of gadgets, and down here we have pop RAX, pop RBP, pop RDI, etc, etc, etc. So all of our cool gadgets are over here, and we can use them as code blocks as previously seen here in this slide. These code blocks in order to run some code and set the first argument. So what we can do now is we can just set out the payload. Then we want to, instead of jumping directly to the win function, what we want to do is we want to jump to the code block that does pop RDI. Then we want to do because now if we have, so you can see the stack layout over here, right? We have the address of pop RDI. Next we want the value. Next we have to put the value that we want to put into RDI, right? Because after the pop, after the red, it will be the top thing on the top of the stack. So we can just put a big number over here. Then afterwards, we can try to jump to win. So if we go into GDB, info functions, we can see the win is over here, and then we can add it over here. So theoretically, that should give us a shell, right? Because we return to RDI, then we pop a value into RDI, then we jump to the win function, and because we have set up the arguments such that the score is very, very large, it will pass this check, and therefore we'll get a shell, so system message. So we can just do ask and send line after name, and we can try to run it. And as you can see, although it says we have won, hit a shell, we are actually crashed. So why is that so? Let's just attach GDB and see what is happening. So I have attached GDB here. And you can see that, apologies, I forgot to zoom in. So we can see that, zoom in here also. So we can see that we have set, actually we need to set breakpoints first, apologies. To GDB red to win revenge, we can do break, win, and then we can, now we can set a breakpoint of win, so we win, and then we can do local attach GDB, and it will attach GDB for us. Good. So now we can see that we have broken that win, and we can step through. Actually, we can just press continue, and we can see that we actually 6F'd, right? You can see stopped at here, reason 6F. If we take a look at the code, we see that we 6F at the move apps. So if you are not familiar with move apps, it is Basically, what MoveApps does is that instead of reading only 8 bytes into address, it actually reads 16 bytes of an address to an address. So this means that when we set up our stack and when we want to use MoveApps, we need to set up our stack to be 16 bytes aligned. So as in like our payload and our stack needs to be an even number. However, you see that however, we see that our payload here, the parts where we are doing code execution, is actually an odd number. So 1, 2, 3. So it's 3 times 8, that's 24 bytes, and 24 bytes is not divisible by 16. So we need to pad it such that it is divisible by 16. So what we can do actually is we can just add a quote unquote useless return gadget over here, and you can just rerun the thing and see that we have one and we've got a shell. Yeah. To provide a bit more of visualization on what's exactly happening, I will show you exactly how the ROP chain works and step through it in GDB. So let me just let me just see which I should break. Yes, I can break over here. So we can set a breakpoint here. Then we can run our solve script with GDB and we hit the breakpoint. So you can see our stack has now been set up. Actually, no, you don't use stack, telescope. So you can see our stack here has been set up with init with our red address being overwritten. And you can see that this is our red gadget, this is our pop RDI gadget, and this is our win function. So we'll just step through and you can see how the stack changes. So now we're on the verge of calling red, and you can see on the stack that our red gadget is going to be called, right? And because now we have executed red, and now we're gonna execute the red gadget. So we're gonna pop another address off the stack. In this case, which is our gift address. You can see on the top here. So let's just step again, and we go into pop RDI. So now, because the address is gone, the pop RDI at the top is our score value. So we'll read that in and hit another red. So now we'll pop this address of the stack into RP, which redirects execution to win. And so therefore, that is how we are able to use return-oriented programming in order to get a shell. And if we just continue and we detach, and here's a shell in ls, and we win. So that is a quick explanation on how we can use return-oriented programming to get a shell in order to do binary exploitation challenges. So now that we know that we can use return-oriented programming by looking for gadgets on the binary in order to pop a shell, now begins the question, right? Is the executable the only binary that exists in our memory? If there are other binaries, can we also use them to our advantage to pop a shell too? So now we introduce the existence of this thing called libc.so, right? So C has a standard library that is known as libc, with the most common implementation on Linux known as glibc. So when we use standard library functions, we load the libc.so library into memory. And because this library is also a binary, we can use the instructions in libc.so to help us pop a shell. However, our plans might be slightly ruined because of ASLR. So here we can see that we're running this pwn challenge baby heap multiple times. And you can see for many of the times, the address at which libc is loaded to is different. This is because address space layout randomization is a feature in the Linux kernel that randomizes the way that key memory areas are loaded into memory. So, for example, your stack, your heap, your libraries, etc., all of these are affected by ASLR. This is to prevent an attacker from reliably redirecting its code execution to a particular exploited function in memory. Because the location of libraries, i.e. libc, are different each time we run the program, we need to know where libc is loaded in order to call it. So that's why we need to leak the libc address in order to get the base at which the ASL base at which it is loaded to. Therefore, we can calculate the address at which we need to call libc at. So we'll just do a quick walkthrough of this challenge called read to libc. It is also available on the CTFD as 6 read to libc. So we can just quickly do pwnit. Here, pwnit is quite essential to do because we're using a libc, right? So, and different versions of libc have different offsets. So we have provided you, if you can see here, we have provided you with the libc version that we are using. And so by running pwnit, you patch the binary here, read to libc patched, to use our version of libc instead. So this is crucial, as if you don't, the binary will use your system version of libc, which is a newer version than what we are using on our server. So in order to avoid discrepancies with regards to offsets, it's highly recommended that you use pwnit to patch the binary in order to load our version of libc instead. So we can just take a look at this in our editor. Just solve.py and zoom in. Yeah, and we can see in main, we just have a very simplistic variable function. Please give your name and some gifts. So this is all pretty standard, right? And so what we want to do is that we want to set up the program in such a way that we're able to call system binsh. So what we want to do is call system binsh. So I'll just type it out here. So this is what we want to be able to do at the end of our exploitation chain. Yeah. So what we can do is that we can just set up the default payload. Then we can do something similar to what we have done, right, with return-oriented programming to set up the RDI in order to point to binsh. So want to make sure that the first argument of system is a pointer to the string binsh. And if you look at that, just nice, our binary contains this very nice string binsh. So what we can do is that we can first we need to search for the gadgets. So we do rp gadget, and once we have the gadgets, we can find for pop RDI here. Then we want to put the address of a binsh inside our stack, right? So what we can actually do, a nice little trick from Pro Tools, is that we can just do next exe.search /bin/sh hex 00. So what this does is that it basically searches so basically exe.search searches the executable for this string here binsh with a null terminating byte, and we basically return the address of it thanks to magic by Pro Tools, and we pack it into our payload. Then we can just next afterwards we want to return to system, but we need to know the address of which libc is loaded to, right? So what we can do, we can actually see here that it actually prints out the address of printf. So if you were to actually run it, see that it prints out this address, which is the address of printf. So what we can do is we can do r.receive until libc. Then we can leak equals to, by converting it similarly to an int, then because it gives the address of printf, right? We want to subtract the offset of printf from our leak. So we minus libc.sim printf. This will give us the offset that at which printf is stored in the libc binary. Then once we have our leak, we are able to do we're able to add the address of system by computing it with the leak. So leak plus libc sim system, and we can add a single line after name payload. So we can run our solve script and see that once again we crashed with the 6F. So if we were to just inspect in GDB, now you see that similar to the previous one, we crashed at the move apps. So this means our stack once again is not 16-byte aligned, and we need to align it with a single red gadget. So we can just go in and find the red and just put it here on top. And then we can rerun our exploit, and we see that we again get a shell. Amazing. So here we can see how we can, instead of just solely using addresses and instructions in binary, we can integrate it with instructions in libc. And instead of jumping back to the binary and relying on binary for everything, we can also cleverly use certain instructions that are already present, certain instructions and functions that are already present in libc in order for us to get a shell. So to once again help you guys visualize, I will show you the stack layout in GDB. So we can break over here. So if we look at the stack, we can see that here we have our red gadget. This is our pop RDI. This is the value we want to pop to RDI, which is, as you can see here, is a pointer to binsh. It's pointer to binsh, which has nicely been resolved for us by GDB for visualization. And next we jump directly to system. So if we just step through, now we call the red. So we go into the gadget pop RDI. As you can see at pop RDI, our our pointer to binsh is the first one on stack. So pointer to binsh will go to the first argument for system, and then we call system. Yeah, so let's continue and see that, yay, we get a shell. Yay, amazing. So that's how we can not only just return to addresses on the binary, but also return to addresses inside of libc. So that concludes our content for day 1. If you have any questions, feel free to drop us a question in Pwn General, or open a ticket and ask us. There are 2 homework challenges available, dog and cat. You can find them on the CTFD. If you wish, you can explore and try to do them on your free time, on your own free time. We'll be releasing the solutions after day 2. So thank you for coming for this day 1 of our Pwn workshops, and see you at day 2.